Okay, so this is going to be a tour of this spreadsheet. This is for looking at a model of a ball going down a ramp, and we're comparing different models, and I'm going to look at the sliding with friction model for this one. But what I like to do with whenever I do any kind of analysis is I make a spreadsheet and I do it in layers. So the first tab is usually my raw data, so it's pretty much just what have I measured, and I've repeated the values here to make it easier to calculate. So we can calculate out the angle as the arc sine of the height over the length of the ramp, and we convert it to degrees. And here's the time measured, and then do about 15 or so trials for each angle. I usually have a tab just for data and no calculations, although in this case it makes some sense to at least calculate out the average speed, from these from this kind of length and time, and then I convert it to meters by divided by 100, and then the final speed is just twice the average speed for that. So that's pretty much my data table, and I have color coded the different angles that I've done. So the next part of it looks at averages of those quantities. So essentially, if you look at this, it's the average of the original data at certain locations. So I'm just going to go back and delete this and just show how I got that, and so I can do equals average, and then go back to my original data and choose the range. And this is for one trial, and that gets me my value. So then for the next trial, I have to select just for that trial again. This is kind of the most manual part of that to get those average values. For convenience, I also put a $ in front of the G so that when I copy that equation over to other parts of the spreadsheet, it won't cause a problem. So when I copied it over here and I just changed the function, it didn't change the column. But you don't need to do that. You can select your own data. And I do the same thing for the angle, doing the average. So this gives us a kind of our best estimate for the final speed across each trial. And then we have to do the uncertainties. So with the uncertainties, we have to have the number of data points, which I use the count function, again, selecting over the exact same data that I select for over here. So notice that the data is the same, it's just the function is different. And I have 15 for most of these and 16 for one of them. I do it with the count, so that way I don't have to count it manually, but you can count it manually, not too big of a deal. The k is 1 plus 20 over n squared, so it's calculated in that way. And then the standard deviation is calculated with stdev.s. Again, over the original data, the same exact data that we have for all of that. The uncertainty in that speed is given by k times s over the square root of n. So it's calculated in that way. Many times with error bars, we're going to use 2 sigma error bars, and so that's just twice this uncertainty. Now we need to look at the uncertainty of the angle, and the way we can do that, this is like for each of those trials, and so I can do one example of each, so I get the angle for each of those. And if you recall, so it's the sine, the arc sine of the height over the length. If our uncertainty is, say, plus or minus 1 centimeter, then what we can do in the crank 3 times is essentially plug in values that make this value the lowest, which would basically be the height is lower by 1 centimeter, but the length of the ramp is high by 1 centimeter. And so we have minus 1 there and plus 1 there. And then copy that down for that. The same thing for the high, it's reversed, so it's the height is adding 1 and the length is minus 1. That gives us the kind of high and low ranges. Excel is going to want not these values, but the difference between that and our estimate. So I do an error bar low value and high value by just subtracting, say, the low from the angle or high from the angle. And so this is going to be used for our uncertainties for the error bars. The next thing we do is we do a data plot. So this is what it's going to look like eventually. But the way you do it is you I like to use an entire sheet for a plot. So here's plot, and I'm going to show quickly how it's done. I do insert. I always do scatter plot, even if I'm doing a line, and then I like to make it relatively big, and then I can go to select data, and then I add a series, say call it my data as opposed to models and so on, and then I'm going to go select the data that I want to plot. I really want to plot these on the X. Notice I'm not including the title here, and then I do the same thing for the Y. Just select that data, and hit OK. And notice we have the markers, and that's okay. And quick check that these values seem reasonable given the values in my data. And they do. So our angles range across from 5 to about 35 or so. And that makes sense. And these are screens. Then I would go through and actually change font sizes and things like that. I'll show you the final product, but that's just easy stuff. The next thing, though, definitely want to talk about error bars. So you go over here and you add chart element, you add error bars, you go to more error bar options. Excel puts some garbage error bars here. It has no idea what to do. So you go to the options, we're going to do custom. So for the speed, we're going to specify both symmetric error bars above and below using the 2 sigma values. So I'm going to go, and for the positive values, I'm going to go here and select the 2 sigma values. Again, remember, I'm not selecting the titles, just the data. And the same thing here for the low. I'm just going to do the same exact values in return, hit OK, and everything's good there. Now I'm going to select the horizontal one. So this is our uncertainty angle. Again, go to custom and specify the value here. The positive value is my error bar high that I calculated, and the low to make the values there low. Okay, and that gets me my error bars for this part. Again, after that, we clean it all up. I'm going to delete this for now because I already did that, and so I increase the marker size, the font sizes. I put titles on the plot. You can find that under chart element. You go to access titles and choose titles for those, and make the font size big for those as well. And there we go. Now onto the models. So I'm just going to do this one model, and this is the sliding reflection model, and the equation for that, you recall, is v squared is equal to 2 times x, which is the length of travel. I convert it to meters, and the whole thing is times g times sine of the angle minus the coefficient of friction times g times the sine of the angle. Notice a couple of things. First off, I said v squared is equal to that, so I do a square root to solve for v, so that's what the predicted speed would be. Second thing is whenever I do the angle, I always have to convert it to radians because that's what sine and cosine are going to expect. And finally, for parameters like coefficient of friction, what I often do is I'll put a label in a cell, and the next cell will have the value, and then when I reference it, I put the dollar signs in front of both the column and the row, and that lets it, when I copy it, for that to be fixed, so that we have that fixed value. And then after I do the equation once, then I can simply take this and grab the little corner and drag it all the way down. And notice what the angles are. The angles are not my data angles. They are from 0 up to about 40. This is about the range of the plot I was doing. But every 0.2 or some small number. It doesn't have to be 0.2. It could be 0.1, 0.5. You want it relatively small and take up a number of rows, so that way the plot will end up being smooth. The other thing you should notice is that I'm getting an error on some of the calculations. And the reason is that with the coefficient of friction, if you look at the equation, if it's high enough, then under the square root it will be negative. And that's because if you get the coefficient of friction high enough, it's not going to slide at all. And so it would predict basically 0 for everything. So we'll leave it there. It just won't get plotted. We'll see how that works. If this is, say, 0, no friction, you'll notice that everything behaves itself I then also duplicate the data plot. So I have a plot with just the data. Now I'm going to duplicate it, and I'm going to add a data range. So I'm going to add the model. So what I do is I go. I've already done it, but eventually I go and I select data and I just add another series. I call it model 2, and then I select the data as that I want. The x values are going to come from this angle, and make sure not to include the title. And the y values will come from here. You include all this. You include all the cells here that you have the error on it, and we'll see why. I made the line a dashed line just in case I'm putting in black and white. I want to be able to distinguish between different models in black and white, but I like the color as well. I also put a label here. You can use a legend if you want to. And this way, I also put a box around it the same color as the line. That just makes it a little easier to read. And if you have more than one model, you can put the labels where it makes sense. Finally, if I go back here and I change the value of the coefficient of friction, you'll notice that the plot updates. Okay? And so for some values, if I put it like, let's say, 1, and I go over here, plot updates to 1 and be a little bit too high, let's say 5, say, and that's going to be really high, kind of a mess. So maybe 1, and as you clearly can see, some values kind of go closer to the data and so on. This one kind of goes under this one a little bit too much, and only goes up above that. So maybe about 0.07 or so might work. Do this by hand. There are ways of automating it, but that's a reasonable thing. That would be fine. Finally, in order to compare the theory to the model quantitatively, not just on the plot, is you need to take and compare the prediction to each data point. So that's where this comparison to the model is. So here I have the actual angles, I have the final species, they're all four data points, so you do the best estimates. I have the prediction, it's basically the same equation, it's copying the same equation. But I'm referencing these speeds, and then I look at the difference between those two, and sometimes it's overestimating, sometimes it's underestimating. And then I look at the difference squared, and the mean squared error is the mean of these differences squared. So you can see it's the average of these differences squared. To calculate out the DIC, I need the number of free parameters. In this case, there's 1. The 1 is this one. It's the one parameter that I need to fit to the data, kind of play around with. If I didn't do that at all, if the model didn't have that, then k would be 0. If you had something like a linear fit with an intercept and a slope, that would be 2 parameters because they both need to be fit to the data. So it depends on your model. And then this is the number of data points that I have here, and then the DIC is calculated as a complete So anyway, this is the tour, and hopefully this helps. And you could even, like with this, you could probably put in the, manually copy the BIC out to a couple decimal places onto the plot, so that way when you do multiple models, you'll be able to see immediately what their BIC values are, which ones are better, and so forth. So, I just noticed that this plot, the font is overlapping a little bit, so I'm going to move that in to make sure that it doesn't crowd that. We want the plots to be as big as you can. Makes it more clear. So that is it. Hopefully that's